Good morning. So I'm happy to introduce the next invited speaker, which is Gabrielle De Lannoy from the Catholic University of Leuven in Belgium. So Gabrielle is their full professor, and she did her PhD in the University of Ghent in bioscience engineering, and moved afterwards to NASA and was working there nearly 10 years. And the NASA main activity was to assimilate remotely sensed soil moisture in global land surface models to overall get an improved representation of the soil moisture of the land surface as a lower boundary of atmospheric models and also for hydrological models. Another important activity was the assimilation of snow information, also to improve, let's say, constraints on the large-scale hydrological modeling. So recently, Gabrielle is also focusing on improvement of land surface models, for example, the inclusion of peatland in land surface models, and is looking to use of vegetation information, and that also in combination with crop modeling. And today, I think we'll talk a bit more about this. So, Gabrielle, please.
Good morning, everyone, and thank you, Harian, for the kind introduction. Thanks for having me here. So today I'll talk about satellite-based soil moisture and vegetation data assimilation in land surface and crop models, and that within NASA's Land Information System. Now, the work I'm going to present today is mainly done by Zenko Heijvaart, Louise Bisgaert, and Nicolo Lanfranco. So these are PhD, postdocs, and even a master's student, but they did great work. So, soil moisture and vegetation are critical variables within both land surface and crop systems. And Inge already has a little bit introduced what crop models are and hydrological models or land surface models. So both are actually very similar, but they're also very different. And that's why we use different modeling systems for these two different systems, right? And so you know land surface models such as the CLM, VIC, NOAA-MP, they model land and water and energy fluxes. If they're good models, they also model the dynamic vegetation, right? Those models, they are designed at a relatively coarse resolution with the idea to provide the best possible land boundary conditions to then ultimately couple to the atmosphere or to an entire Earth system model so that we get the entire system simulated right. By contrast, crop models, they're designed at a field scale initially, and their focus is on water use, water need, and then ultimately how much yield do we get from this particular crop, right? So they have a different focus. In any case, the Land Information System from NASA that used to only host land surface models, that now only also hosts one crop model, the one that we develop and maintain for FAO, and that's the aquacrop model. So that model from now on can be run globally at any spatial resolution, any spatial domain, as long as you give it spatial maps of crop parameters, soil parameters, topography, and all those other things that you can give. Yeah? So both these modeling systems, they can now be run with reanalysis forcings. For example, MERA2 or ERA5. You can run ensembles, and you can run any type of data assimilation with it. So the data assimilation I'm going to talk about today is soil moisture retrieval data assimilation, leaf area index retrieval assimilation, and vegetation fraction cover data assimilation, right? The assimilation technique I'll talk about is the ensemble Kalman filter. There are different options, but for today, it'll be state updating only. So those two systems, land surface systems and crop systems, they have similar state variables, and those are, of course, surface soil moisture, root zone soil moisture, and vegetation. I know for sure that all of you know these variables, but just let's reflect on them. Surface soil moisture immediately responds to the atmosphere, right? You have those peaks that are responding to precipitation and then immediately declining again as soil moisture is drying out. Root zone soil moisture reacts much slower. It has a much longer memory, right? Surface soil moisture in a model is determined by the parameters in it, and that's very important. It's bounded, both in the upper and the lower values, by soil parameters. So it's a model attractor in there. So you cannot stick any type of soil moisture observations into that model, because otherwise you'll push it out of its equilibrium, and that's not the idea. The same with satellite retrievals of soil moisture, they have their own bias. So you need to reconcile those two sources of information. You need to take out the bias between the model and the observations before you do any soil moisture data assimilation. I'm talking about long-term soil moisture bias that need to be removed. Yeah? So that's state of the art. We all know that. I'm not going to come back on that, but assume that as known, right? The root zone soil moisture, just like surface soil moisture, is double-bounded. It interacts directly with the vegetation. So there, an update in surface soil moisture will trickle down to the root zone and then also affect the vegetation. Now, vegetation is a different type of variable than surface soil moisture in that it's a cumulative variable. And so if you miss a stretch of warm or cold temperature, you may actually introduce a bias just because one short event introduced that bias, but that's not a long-term bias. And that's the reason why if we do vegetation data assimilation, you don't necessarily need to do bias correction, although, and it's typically not done in literature, but I'll show you that in some cases you actually should consider doing so. Yeah? So for vegetation data assimilation, the take-home is we don't know if you need to do bias correction, but I'll show you that probably you better do. For soil moisture data assimilation, you should always do some bias correction. For those who don't know what data assimilation is, just really quickly introducing, we have observations, they're sparse in space and time. We have models that are complete. Both sources have their own uncertainties, and through data assimilation, you try to get the best information from both to get the best complete image in space and time of the world. You also only typically see some variables and not all the variables. For example, you see surface soil moisture, you don't see root zone soil moisture, right? And so data assimilation can propagate that information. With an ensemble Kalman filter, we produce an uncertainty simulation. So we have the model in different ensembles. Whenever there's an observation in red there available with an uncertainty, we assimilate that information, we reinitialize the model, and then let it run forward again. Yeah? So through that system, we go from observed information to unobserved information. You could possibly go from coarse to fine scale, and you go from intermittent observations to a continuous, complete image of the globe. Okay, starting with soil moisture data assimilation. So you go and we assimilate surface observations into this model, and the data assimilation will take that information and then very briefly forget about it, right? The result will be that deeper soil moisture is also responding, but it'll take somewhat longer, it'll have a somewhat longer memory of that update. The idea is that we go, again, from surface soil moisture to root zone soil moisture and then to vegetation, and thereby we would improve fluxes, evapotranspiration, discharge, if the model coupling is right. Yeah? Ultimately, that should then help to improve the weather, or, for example, hazard predictions such as landslides or droughts. And I'm going to assume today that soil moisture data assimilation is state-of-the-art. We know how it works. Again, it means that we only assimilate anomalies, we remove the bias. Assuming that we know how to do this offline data assimilation, and we really do know, right? There's plenty of papers on that. Let's take one step further. How can we now use that data assimilation, those data assimilation results in terms of soil moisture to improve or at least have an impact on our atmosphere? So we're going to use the results from an offline data assimilation system, and we're going to feed that into an online system that is a coupled land-atmosphere system. There was already some allusion to such a system before. Yeah? So we're going to run NOAA-MP in offline mode. We're going to force it with MERA2, and then we're going to use data assimilation next, where we assimilate SMAP level 2 data with quality flags, all the proper way of doing SMAP data assimilation. It's at a 25-kilometer resolution. We have 36 ensembles, and we're going to update the soil moisture and LAI. We also perturb the forcings. All these variables are perturbed, right? But we are only updating soil moisture and LAI. And we then have a model simulation, we have a data assimilation simulation, and those outputs we're going to feed in that coupled system. So again, this is the idea. In brown, you have the model only without observations assimilated. In blue, you have model simulations with data assimilation, and every 14 days, we're going to initialize a coupled system, right? Where we don't give meteorological forcings, but the system is computing the meteorological forcings. And from that, in the coupled system, we now have a 14-day forecast, right? Okay. So this is the idea for one time step. So one of those 14-day forecasts at one time step, the 1st of August 2018 here, we have this difference in initial conditions of surface soil moisture. So because of the data assimilation. This is the land-only data assimilation. And you see some areas are wetter, other areas are drier, right? That's just the effect of the data assimilation. We have a consequent effect on the LAI, and here on a difference in the evaporative fraction. So this is the difference in initial conditions at the land. Now we feed that to the coupled system, and we produce a 14-day forecast of all the different variables. I'm only showing you two, but if you look into Zenko's paper, you see many different variables, right? And you see if we force it with the model-only soil moisture, we get this profile of soil moisture, profile prediction, right? And if we initialize with the data assimilation, we get this one. And you see with the data assimilation, we get an earlier precipitation event than with the model-only initialization. If I take the average over this entire 14-day for all the pixels, you see here the impact on the difference in soil moisture. Yeah, so it's a bit of a mirroring of that, plus noise because of the precipitation events that are different because there's circulation going on. Yeah. The effect of the difference in soil moisture also translates in the fluxes. So this is, for example, in terms of latent heat flux. Okay, now you have to follow me because I'm going to bin these difference in soil moisture, and I'm going to associate the average difference in soil moisture, latent heat flux, and all the other fluxes in one graph. So that's this one. So here I'm binning my difference in initial conditions, and I'm showing you the resulting difference in atmospheric variables. So this is for the latent heat, sensible heat, planetary boundary layer height, the temperature at 2 meters, and the humidity at 2 meters. And what you see nicely, so over entire CONUS, right? All of CONUS, and the 3 summer months. And for all those 14-day forecasts, I'm showing you that difference. And you see nicely that if we increase our soil moisture, we have more latent heat than if we decrease, we have less latent heat. So that's what we expect. But this is the impact of the data assimilation, right? So the data assimilation impact, the data assimilation change results in an impact on the atmosphere. Okay, step 1. Step 2 is that the impact on the atmosphere does not only depend on our initial conditions on land, it also depends on the land-atmosphere coupling. And that's maybe something new for some of you. If you're interested, I have the equations. This is the coupling for the model-based coupling between surface soil moisture, latent heat, surface soil moisture, sensible heat, planetary boundary layer, all these different atmospheric variables. And you see that for the summer, well, you have different hotspots, right, where you have different strong coupling between those variables. So I know a priori where the model tells me that the coupling is strong and not. Right? So I can possibly use that to target where I want to do the assimilation. That's our hypothesis. And I'll show you what comes out of this. So if I now bin these maps for their coupling strength, and I put those on the x-axis, so this is the coupling strength between surface soil moisture and latent heat, and then I look at the impact on my atmospheric fluxes, you see that as the coupling strength increases, that's to the left, stronger negative is a stronger coupling strength, then the impact on my atmosphere increases. So the reality is, if I know where the coupling is the strongest, I can target those regions for data assimilation. And if then I have large updates in soil moisture, which I know from the previous slide, you know that you'll have a good impact on the atmosphere, right? So I think that is really good to sort out where we can most efficiently do data assimilation. So that's moving soil moisture data assimilation one step forward. Now I'll go to vegetation data assimilation. As I said before, it could be that you have bias or not, and here we don't know exactly if we need to do bias correction or not. But the idea is the same. You assimilate, for example, vegetation cover, and you want to improve, for example, evapotranspiration. Or if you have a crop model, you may want to improve your yield. And that is still a big step forward. I'll show you where we are with that. So this is if we assimilate LAI into the NOAA-MP. NOAA-MP dynamically simulates vegetation. We do that for 17 years, and it's a CGLS product. Again, 25-kilometer resolution. And I'm showing you relative differences of LAI, GPP, evapotranspiration, and then soil moisture in different layers and runoff. These upper plots are on overall orange, meaning we're everywhere decreasing our LAI, GPP, and evapotranspiration because there's a bias between the model and the observations, and we're not resolving that bias. We're not taking it out. Yeah? The consequence of doing this type of data assimilation is that we are increasing our soil moisture everywhere because we're removing plants, right, our leaves. We're increasing the soil moisture and we're increasing the runoff. So the question is this actually a good thing? There's one exception here, the Nile Delta. It's hard to see, but there you don't have orange, it's actually green. We're adding vegetation. You know already why we're not modeling irrigation in the system. So the data assimilation is putting vegetation in the Nile region. Okay. The black line here is our assimilated vegetation, and we're going to assimilate the blue observations. This is in Spain. And you see that these observations are much lower than our model. So if we do it without bias correction, you see this sawtooth pattern. And that's typical for a biased system. The consequence of that, so the blue line, is that the soil moisture goes from black to blue and becomes wetter. If we do bias correction, CDF matching, seasonal scaling, then actually our curves remain closer, like the orange and the green remain closer to the model, and soil moisture also remains closer to the original situation, right? This is for the Majada site in Spain, right-hand side for the Nile Delta, where we don't simulate any LAI because it's all dry, but the observations tell us something is growing, and you see this really ugly sawtooth pattern. If you see that in literature, please say something as a reviewer, because really it's not a good idea. You're pushing your model in all different directions, it's not good. So the LAI is going wiggle, wiggle, and the consequence of that is you're trying to grow vegetation and you're completely depleting soil moisture in an area that's heavily irrigated. So not right. So that's why I would say, really, we need to do something about this vegetation data assimilation, do some bias correction to get the system right. But ideally, where we need to go is to do, of course, a multivariate, multi-sensor data assimilation where we do both LAI and soil moisture data assimilation. I'm showing you the LAI data assimilation and the soil moisture data assimilation. If you do LAI data assimilation, the impact on soil moisture, evaluation on soil moisture side is minimal. If you do soil moisture data assimilation, you're on average improving your soil moisture relative to in situ data. Yeah? If I do LAI data assimilation, I improve my GPP overall over the map. If I do soil moisture data assimilation, I decrease my GPP estimation over the entire map. If I show this in a box plot, you see for soil moisture data assimilation, I improve my performance in soil moisture. If I do LAI data assimilation, very little impact on soil moisture with this model. If I do LAI data assimilation, if I do soil moisture data assimilation, I degrade GPP. If I do LAI data assimilation, I improve. Now, if I combine both, if I do both soil moisture and LAI data assimilation, then you get this orange box. Forget about these ones, I'm not going to explain it. You get this one, and you see that you inherit the improvement in soil moisture data assimilation, right? And if I combine soil moisture and LAI data assimilation and now evaluate the GPP, I'm actually inheriting my GPP improvement, which is really nice, right? So I get the best from both worlds. I can also see that this joint data assimilation is really improving things, I can also see that in my innovations. Innovations are the differences between my model forecasts and observations over a time series. This is averaged over the entire map. This is a difference between innovations from the joint data assimilation minus those from the soil moisture data assimilation only. And you see that there's very little difference there. But if I look at the difference in the innovations from the joint data assimilation for LAI, so LAI plus soil moisture, but I'm looking at the innovations in terms of LAI, and I subtract the innovations for LAI when I only do LAI data assimilation, you see that you have larger innovations if you only assimilate LAI. Your innovations are smaller if you jointly assimilate soil moisture and LAI, meaning that the soil moisture data assimilation is already helping you on the right way, and the LAI data assimilation is only adding a little more extra, right? So both are working in the same direction, which I think is really nice. To end, I'm showing you some new results on vegetation data assimilation in crop models. Our team is really working towards large-scale crop modeling, data assimilation at high resolution. We have all the infrastructure set up. It took years to get there, and now we are very carefully tuning every little bit. So this is a first study over the Piedmont area that is northwest in the Po Valley of Italy. The Italian people will know more about it than I do. That area has a lot of winter wheat that is cultivated there. And we're simulating here at 1 kilometer resolution. So now we're really going to the fine resolution. This is, for example, 1 kilometer grid cell. Within that 1 kilometer grid cell, we have 9 pixels of F cover from satellite data, so high resolution satellite data. We're assuming that each 1 kilometer pixel represents only wheat, winter wheat crop, right? But in reality, that wheat field may move within the 1 kilometer pixel, yeah, because of rotation. The data that we have for validation are yield data at the municipality level. And municipalities are these irregular shapes, right, these, that cover more or less pixels. And you just get one value of yield, but you don't know where the fields are. And the fields may actually just be moving every year, right? So it's not ideal data, but if you look long term, if you take an average, you see some yield patterns, right? So the goal is to assimilate F cover, vegetation cover, at a very high resolution, and we hope to improve the yield. That's the ambition. So we'll run a deterministic run, an open loop ensemble run, and a data assimilation run. And this is for 1 pixel in the Tortona municipality right here. You see how canopy cover is moving, right? Going up and down with a maximum of 1, because that's the canopy cover state variable. And the observations in black are the satellite observations. Every year, this curve represents different fields, right? Because the fields within our 1 kilometer, this is 1 kilometer pixel, but within this 1 kilometer pixel, the fields can shift. Yeah? And so we're assimilating only the winter field, the winter wheat data within that pixel. So for example, let's focus on this year where the changes are most dramatic. So you have the deterministic run, you have the open loop run with its uncertainty next to it, and then you have the data assimilation run, which is nicely tracking the observations. So by design, we are following our observations. Not so by design is that also we're improving our biomass prediction, because the next time series is biomass. This is deterministic and open loop, and then the orange is the data assimilation. So very nice. We are updating our biomass in the right direction. Then the next figure is the yield. We have very little variability in yield. Don't look at the black dots yet, because you cannot compare them. So these are municipality data, whereas this is a single pixel. What you see is that the variability in the yield is very low. We actually hit the absolute value of yield pretty good, but the variability isn't simulated well. And then by assimilating the F cover, you again see this impact on soil moisture. So you feel me coming. Ultimately, even for crop data assimilation, we'll need to do crop soil moisture data assimilation and crop vegetation data assimilation. Okay, so now you may wonder, what is the impact on yield? Here we go. We have the difference between the observed yield at municipality level and the modeled yield, so aggregated now at the municipality level, and the size of the dots tells us how many samples are there per year. So each dot is 1 year, and the number of samples are the number of fields in that year. Our model hits the absolute value, pretty good. It doesn't do well at spatial variability. Why is that? Because we assume a homogeneous fertility, and within this small area, we don't have the fertility levels right. If we do data assimilation, and if we would focus only on the bigger pixels, we improve our correlation, but if you look at that total value, it's only a small improvement. So we have some work to do, and that is because state updating alone will not work with crop models. We'll also need to update parameters related to, for example, fertility. Okay, brings me to the conclusions here. For land surface data assimilation, this is really state-of-the-art. We know what we're doing, especially with soil moisture. Vegetation, I think we have still some work there to optimize that. But ideally, we combine both, and we start looking more at the impact on atmosphere and other variables. Crop data assimilation is still in its infancy, plenty of work to do there, but we're going in the right direction in terms of biomass, still quite some work to do on yield, and we think that we need to do parameter updating there. One last request, if anyone has really good yield data, we would be very happy to work with you because they're very hard to get. So please come and find me if you have any. Thank you very much for your attention.